Today we are going to talk about how to determine the quadratic equation if the zeros or the roots or the solutions are given. Just to remind you of different forms of a quadratic equation, we said before that the quadratic equation can be expressed as standard form, which is y equal ax squared plus bx plus c, which is called the standard form, or it can be expressed in vertex form, which is a times x minus h squared plus k, which is the vertex form. And the last one, it can be expressed in x-intercepts or factored form, which is a times x minus r times x minus s, where r and s are the zeros. Remember, the standard form was good because by looking at it you could see that c is the y-intercept. Vertex form was good because the vertex was at the point h and k, and the factored form was preferred because r and s were the zeros or the x-intercepts of the quadratic. Now in this lesson we are going to emphasize on the factored form, which is y equal a times x minus r times x minus s. If the x-intercepts or zeros are given, this means that r and s of the quadratic are known. Since the factored form has three variables, a, r and s are given, then we have to find a. Now to find a, we have to have another point on the parabola to solve for the unknown a. So in this case we need three pieces of information given. In fact, if you look at any form of quadratic, you can see that there are three unknowns here, a, b, c. In standard form, ahk in vertex form, and ars in factored form. So if three pieces of information is given, then we can find the quadratic form of the equation. In the first example, we have a parabola or quadratic function which goes through the points 4, 2, or points 4, 2 are the zeros or the x-intercepts of parabola. We are supposed to find the equation of the family of quadratic functions that satisfy this condition. If we roughly draw the points, this is, let's say this is 2 and this is 4, then our parabola, depending on the sign of the leading coefficient, must go through these 2 points. Now the only thing is that the graph that we have here is not unique. I can have another parabola going like this, or I can have another parabola going like this one. So there can be infinite number of parabolas going through these 2 points, 2 and 4. The collection of all these parabolas, we call them a family of quadratic functions. So all these three that I've drawn here are members of the same family. But what is the exact family? The family is y is equal to a times x minus 4 times x minus 2. You can see that this type of family of parabolas they satisfy that zeros or x-intercepts given 4 and 2, because if I substitute 4 and 2 in this equation, I will get 0. So to identify a unique member of the family, we need to find A. And based on this problem, A is not given. So the best we can do is just come up with different members of this family. The next example is the same thing. This time we have the zeros or x-intercepts 0 and -5. So the family becomes y is equal to a x minus 0 times x minus -5. X minus 0 is just x. X minus -5 is x plus 5. So this means that y equal ax times x plus 5 represents all the family members that satisfy this condition. Now, if I want to plot it again, 0 is here, -5 is here, then you can have, a member going like this, another member going like this, another member going like this, and so forth. So infinite number of parabolas can be drawn satisfying this condition. To uniquely specify one parabola, I need another point to specify what the value of A is. The next one is -3 and 3, and this is going to be y is equal to a times x minus -3 times x minus 3, which is going to be a times x plus 3 times x minus 3. If we expand these two brackets, I'm going to get a times x squared minus 9. Again, this represents a family of parabolas going through the points 3 and -3, but to specify a unique family member, I have to have another point to find the value of A. The next example is a family of parabolas that they have only one x-intercept, which is equal to 6. This means a case like this one. If this is 6 here, then you will have a parabola like this one, or a parabola like this one, or a parabola like this one, or like this one, as long as there is only one x-intercept. So the equation of the family of parabolas is going to be y is equal to a x minus 6 times x minus 6. Remember, when there is only one x-intercept, this means r is equal to s is equal to 6, which is a times x minus 6 squared. In the next example, we have to find the equation of a quadratic function if the zeros are 2 and -2 and it goes through the point 0 and 3. So the family of quadratic is going to be y is equal to a times x minus 2 times x minus -2, which is going to be a times x minus 2. X minus -2 is x plus 2. If you expand this one, you get a times x squared minus 4. Now, again, this is the equation of a family of quadratic functions because a is unknown. To find a, I need another point, and the other point is given here, 0, 3. So when y is 3, x is 0. Now 0 squared is 0, 0 minus 4 is minus 4, so you get this is equal to minus 4a So a is 3 over negative 4. So we get y is negative 3 over 4 x squared minus 4. This is a unique quadratic equation which has zeros 2 and negative 2, and it goes through the point 0 and 3. The next example, we have a double zero. This means that it has really only one zero, but both of them are equal. X equal to negative 2 and goes through the point 3 and 10. Again, we are going to write the family of quadratic equations as y is a times x minus minus 2 times x minus minus 2. Remember, both zeros are the same. Now, minus minus 2 is going to give you positive, so it's going to be a times x plus 2 squared. Now it goes through the point 3, 10. So when y is 10, x is 3. Now 3 plus 2 is 5. 5 squared is 25, so we get 25a. Now isolate a by dividing by 25, so a is 10 over 25, which is the same as 0.4. So we say that y is 0.4 x plus 2 squared. Again, this equation here is the family of quadratic that has a double zero at x equal to negative 2. This equation is a unique member of this family which goes through this point. The next example is a little bit more complicated. Remember, as I mentioned before, in this course, you are not supposed to simplify square roots by using your calculator. You just leave square root the way it is. We have a quadratic function which has two zeros, 3 plus square root of 5 and 3 minus square root of 5, and goes through the point 2 and negative 2. Again, as usual, we're going to write the family of quadratics as y is equal to a times x minus 3 plus square root of 5 times x minus 3 minus square root of 5. Now I'm going to expand negative inside the bracket. Here I get a times x minus 3 minus square root of 5 x minus 3 is plus square root of 5, because negative times negative gives me positive. Now I'm going to put a bracket around these two terms. You either have two options. You can expand these two brackets and you're going to get the same result that I'm going to get. Or you can use the fact that if this one is a, this one is also a, call this one b, and this one is going to be b. Now, a minus b times a plus b is going to give you a squared minus b squared, difference of squares. So I can write this one as a, open bracket, x minus 3 squared minus square root of 5 squared is going to give me 5. Now I'm going to expand x minus 3 squared. I'm going to get x squared minus 6x plus 9 minus 5. This is the same as x squared minus 6x plus 4. So this is my family of quadratics, but it has to go through the point 2 and negative 12. So I'm going to say negative 12 is going to be a times 2 squared minus 6 times 2 plus 4, which is going to be a times 2 squared is 4 minus 6 times 2 is 12 plus 4, which is going to be 4 plus 4 is 8, minus 12 is minus 4. So minus 4a. Now divide by minus 4a, both sides. From here I get a is equal to 3. So I get y is equal to 3 times x squared minus 6x plus 4. So again, our family of quadratic is going to be this one. And to find the unique quadratic equation that goes through this point, I'm going to substitute this point back in this equation to find a, and I found a to be 3, so this is going to be the equation of the parabola that has these two zeros and goes through this point. In the next example, which is a word problem, we have the opening of a tunnel which is in the form of a parabola. So let's draw this situation. Let's say this is your x and this is your y-axis. Now let's assume that the opening looks like this one, roughly. We know that the parabola, the width is 32 meters. So this is 16, this is negative 16, and this is the origin here. Now we have 2 points on the ground which is 4 meters from each side. So this is 4 meters here, and there is another point which is 4 meters from the other side. Now the height here is 6 meters. So this is 6, this is 6. Sketch a graph. This is our graph. Just remember that I can draw the graph so that the opening is going to be, let's say, this way. So there are infinite number of ways we can draw, and this means that there are infinite number of ways we can represent the equation representing the opening of the tunnel. So if your solution looks different from my solution, it doesn't mean that your solution is incorrect or mine is incorrect. It all depends how you initially draw the setting here. So in my drawing, I'm setting the origin to be halfway between the two sides of the parabola. In the second part of the question is asked to determine the equation of the function that models the opening of the tunnel. So we know that the zeros of the parabola are 16 and negative 16. So the family of the parabola or quadratic equations is going to be y is equal to a x minus 16 times x minus 16, which is going to be a x plus 16 times x minus 16, which I can write it as a x squared minus 16 squared, which is going to be a x squared minus 256. Now to find the a, I'm going to use another piece of information which says that the parabola goes through these points. I can pick any one of these 2 points. Let's say I pick the right side. The right side, the coordinate of this point is going to be, if this is 16 here, and this is 4 meters to the left, this is going to be 12. So my point is 12 and 6 here. So I'm going to sub it back in this equation here to find a. So I'm going to say 6 is equal to 12 times a times x is 12, so 12 squared minus 256, which is going to be a times 144 minus 256. So a is going to be 6 divided by 144 minus 256, which is going to be 6 divided by negative 112. Divide numerator and denominator by 2, you get 3 here, you get negative 56 here. So a becomes negative 3 over 56. So our equation becomes y is equal to negative 3 over 56 times x squared minus 256. Which makes sense because the leading coefficient is negative. This means that the parabola opens downward, and if you look at this parabola, it's opening downward. And if we substitute 16 and negative 16 for x, you can see that it becomes 0. In the last part of the problem, it is asking us to find the maximum height of the tunnel, which is another way of saying what is the y-coordinate of the vertex. We know to find the x-coordinate of the vertex, we are going to find the average of x-intercepts, which is negative 16 and 16. So we are going to say v sub x is going to be 16 plus negative 16 divided by 2, which is going to give us 0, which makes sense because the vertex falls on the y-axis, which means the x-coordinate of the vertex has to be 0. Now I'm going to substitute back x equal to 0 in the equation to find the y-coordinate. So v sub y is negative 3 over 56, 0 squared minus 256, which is 0 squared is 0, and negative 256 times negative is going to give me 3 times 256 positive over 56, which when you use your calculator, this is approximately 13.71 meter. This means that the height of the tunnel is 13.71 meters.